Now we're going to see that despite the different frequencies made and different formants for different vowels, that speech sounds are actually not very consistent. In fact, they are highly variable. One reason for this is that speech sounds are very fast, and that leads to something called co-articulation. We are articulating different sounds together. In other words, we don't make different speech sounds independently of each other. Instead, the successive speech sounds overlap each other. Part of this is just the inertia that prevents our tongue, lips, and our jaw from moving too fast. So if we're saying 4 words a second, like your textbook mentions, that means we're forming all the phonemes of a given word within 250 milliseconds. That's pretty fast, especially if you think about how many speech sounds, how many phonemes are in a word. And so what happens is that experienced talkers position their tongue and other aspects of the vocal tract in anticipation of what the next consonant or vowel is going to be. And this causes co-articulation, the blending of speech sounds. Here's an example. Here's a statement: we were away a year ago. And here we can see the spectrograph made when an individual says this. And so we have frequency on the y-axis. Now the colors here are going to indicate the frequencies that have the greatest representation, that are the strongest in these speech sounds. And so the reds are going to be the indication that those frequencies were really strong. And so those are going to illustrate our formants and our formant transitions. Now I want to point out this particular phoneme, and we see that there are 3 uhs here. We were away a year ago. In these 3 cases, we're really making the sound. But let's look at how different the frequencies made in this vowel are. So in this first example, we have a very strong low frequency and then another one. And then here we see a diagonal transition down, and then this higher frequency transitioning up a little bit as the formant transitions to the consonant W here. Here we see the low frequency, but this next one is not quite as strong. And then the location, the frequency here is slightly different than it is here, isn't it? And yet here in the in ago, we see it's again different. So these middle frequencies are different than what we see here and different from what we see here. And that is evidence of co-articulation. Those 3 phonemes sound the same to us, but they're not the same. And so what happens is that this means that our brain is doing something to these sounds so that they are perceived to be the same even when they're physically different. So phonemes, because they're not produced separately from one another, they're produced simultaneously because of just how fast we speak, it means that our intention to produce each phoneme distinctly is not able to really be successful. Because if your tongue is making a D sound just prior to an E sound, like in the word deer, well, that D sound is going to be affected by the fact that in the word depth, we're transitioning not to an E sound, but to an sound. And that means that the position of our tongue as we form the D is going to be a little bit different in depth versus deer. And yet, in both cases, we perceive those Ds as being the same. So here's an example of co-articulation, the word bag. So the B affects the first 2/3, the vowel affects the whole thing, and the G sound affects the last 2/3. These three sounds are being blended together. And here we have D as in deer versus duh. See how they're physically different? Different sounds are actually being made, but we hear them in both cases as the same sound, the same phoneme. And here's some more examples. Here we'll have 3 words with the consonant B, and yet we can see that the consonant sounds, these formant transitions, are all a little different, aren't they? So if we think of the B as being the first part of this, well, gosh, this looks pretty different than this, doesn't it? So how do we deal with all the variation in these speech sounds? We use something called categorical perception. We perceive categories of sounds. So sounds in between a D and a T are perceived as either one or the other, not as somewhere in between. In other words, the sounds are categorized and not treated as existing along a continuum. It's kind of like if we're watching a bicycle race. Each cyclist is categorized as either fast or slow, but maybe the exact speed they're traveling is not recorded. That would be an example of using categorical perception. It's the opposite of using a continuum where the exact speed would be recorded. So we don't perceive the exact frequencies made when we make A, D, or T. Instead, our brains categorize a range of frequencies as either D or T and never something in between. Here we see an example of categorical perception in detail. So the sound ta versus the sound da, very similar. But what is different is that in the sound ta, we don't start seeing these stripes here, these vertical striations that sort of start forming these stripes. Those vertical striations reflect the beginning of voicing, where the sound is resonating through our vocal cords. And that happens after about 80 milliseconds after we make the initial sound in ta, but it happens within 5 milliseconds, much faster, when we make the sound da. So here we can see these vertical striations kicking in right away. And that difference is the difference between a ta and a da. And here we have a really interesting experiment. So using software, the voice onset timing was gradually changed from 0 to 80 milliseconds. And it turns out that regardless of the exact timing, if it was short, participants always heard da. They couldn't tell these different da varieties apart. They always just sounded like da, even though the timing of the voicing was gradually changed. They did not detect any of these differences. And then all of a sudden, there's this threshold that gets crossed. And all of a sudden now that sound might sound the same as a da, but it might sound different than a da until we cross this threshold. And then once again, after the voicing gets long enough, every single sound sounds like ta. So this supports the idea that even though these sounds are changing gradually, what we hear is either a da or a ta. And then during the transition, when we're very close to this threshold, we will hear one or the other. And it won't be very consistent. But within this range, where the voice onset timing is very short, we always hear da. And when it's very long, we always hear ta. And so that suggests that there's this phonemic boundary. Anything before the boundary will be perceived as a da, and everything after the boundary will be perceived as a ta.